I'm going to take a two-dimensional region bounded by these three curves, which is shaded here, rotate it around the x-axis, and then calculate the volume using the shell method. So I'm going to use cylindrical shells. When I rotate this around the x-axis, I get a symmetric piece over here. And I've got now a 3D object that looks like a little cylinder with a cone hollowed out of it. And I could do this with the disc washer method, but for now I want to do it with the shell method. And the idea is I build these little cylindrical shells from the inside all the way out. So if I grab just a random one, it's going to look something like this. I have a very small thickness. That thickness is going in the y direction. I'm going to call it delta y because we're going to fill this thing up with these cylindrical shells, and if delta y is wider, I get a more rough approximation. If it's smaller, I get a more fine approximation that has less error. And to get the exact volume, I take the limit as that delta y shrinks down to 0. So what I need to do is think about how to find the volume of one of these shells on its own. Then I can add up the volumes of all the shells to get the approximation. And then that becomes the integral when I take the limit. So one of these shells, if I draw it over here, looks something like this. And I know this width is delta y. What I'm going to do is cut this thing open and make it a long rectangular strip. So if I cut it open, like for example right here, then if I unfold it, it will look something like this. If I take the two pieces that were touching there, put them on the edges, and it looks something like this. It has a little bit of thickness. And that little bit of thickness is the length delta y. The purple length is just the x value along this line, y equals 2x. So this is the x value. And x, if I solve for x on this line in terms of y, that's y divided by 2. And then this long length is the length that I get after I've unfolded this. So it's the circumference of this circle, which is pi times the diameter, or 2 pi r. R is going from the center of the circle up to the top. So that's just the y value. So 2 pi r, this long length, I could also think of as 2 pi y. And these shells change as I move from left to right or from the center up to the top. As you vary x and y, then you get different values because you're taking your values along this line. All right, so before I actually get to the integral, before I take the limit, my approximation looks like this. I'm adding up these volumes, and the volume is just length times width times height. So 2 pi y times y over 2 times delta y. Then when I take the limit, as delta y goes to 0, this pops into an integral. I'll combine these two. So y times y is y squared. 2 divided by 2 is 1. So I'm just going to get pi y squared out of this. dy. And then I will integrate from y equals 0 up to y equals 10. As I start in the middle and come out to the top, the bottom edge, or the bottom half of these shells are going to pick up the volume on the bottom. So I'm just going from 0 to 10, not negative 10 to 10. Now I find the antiderivative and plug in the bounds. And 10 cubed is 1,000, so I'm getting 1,000 pi over 3 for this volume.